that combine several weak learners to boost the performance of the strong classifier. So there are several famous algorithms belong to the ensemble family. So let's talk about, we have described ADA boost. This is one of the most famous boosting algorithms. ADA boost maintain a weight distribution over training data. While iteratively update the data weight, we can select strong and complementary weak learner to construct a final strong classifier. So this is the reason why this algorithm is called ADA boost. It is adaptive boosting. It is a boosting algorithm that maintains an adaptive data weight for selecting weak learner. ADA Boost has its theoretical support, and it is simple, effective, and accurate. Not all, we also we talked about the detail of ADA Boost last week. We also illustrate how to apply ADA Boost to carry out face detection. We leverage our prior knowledge about face detection. It is allowed to develop suitable features, rectangle features. Each rectangle feature can be used to control a weak learner candidate. Totally, there are more than 160,000 weak learner candidates. ADA Boost can effectively select just 200 weak learner to year strong classifier. So this is what I told last week. We also talked about decision tree. Due to the time limitation, I have not completed the description of decision tree. In today's lecture, I'm going to give a quick review of this decision tree. Then I will complete the introduction to decision trees. Then I will describe two other famous algorithms, ensemble algorithm called the baking and the random forests. We will use the two ensemble method to construct a set of decision trees such that the performance of a single decision tree can be improved and the resultant classifiers are more robust to data noise. If time allow, I'm going to give a quick introduction to kernel methods. Also, our teaching assistant Jimmy is going to announce homework number 3 in the last sessions. Okay, let's have a quick review of a decision tree. Actually, decision tree is a hierarchical model for supervised learning. It implements divide and conquer strategy to carry out classification or regression. We know a decision tree has a tree-like structure. The node can be divided into two types, including decision nodes and leaf nodes. For each decision node, we use M to denote this decision node. For each decision node M, it implements a decision function Fn of x. Given a data point as input, the output of Fn is the index of the branch. In other words, Fm is used to divide the data point reaching node M into several subsets, and each subset is used to construct a specific branch. So there are two or more branches associated with each decision node. And the number and the decision the number of branch and the decision boundary is controlled by this decision function. The second type of node is called a leaf node. Uh, there is no decision function inside a leaf node. Instead, each leaf node is associated with a prediction outcome. For regression problem, the output of a regression is a regression value, a real value. So each leaf node for regression is associated with a constant. This constant is used to indicate the regression result, a real value result. For classification, each leaf node is associated with a class label. So we can realize the category that the input data point belongs to. A decision tree is composed of several decision nodes and the leaf node. For input training or testing data, we feed this training data to the root of this decision tree. Since the root is also a decision node, so we can use the associated decision function to realize which branch this data point belongs to. So we will move to one of the branches. The process is repeated from the root until we reach a leaf node. Since each leaf node is associated with a prediction output, a constant for regression or a label for classification. So we can realize the prediction output of this data point. Okay, so this is a summary. This is a summary of a decision tree. Here is an example. In this decision tree, there are two decision nodes, each of which is associated with a decision function. So this is the first decision function, and this is the second one. As you could see, there are three leaf nodes in this decision tree. So there are three corresponding output. So this is the decision region for the first leaf node, for the second leaf node, and the third leaf node. Okay, so here is an illustration about the operation of a decision tree. If we want to use a decision tree for regression or for classification, the most important task is to control a decision tree. We know decision tree is a supervised machine learning methodology. Therefore, it is required to have a set of labeled training data. So we have the label for data points, and we also have the corresponding ground truths. They could be, because a decision tree could be used for regression or for classification. So the ground truths could be the regression ground truths or classification ground truths. In the following, let's focus on classification. However, the same process could be appropriate and modified for a regression problem. Given a set of training data, we want to have an optimal decision tree. We want to find a compact and accurate decision tree. However, finding the smallest or the most compact decision tree is an NP complete problem. We cannot efficiently control an optimal decision tree. Based on this, due to this constraint, greedy measures are widely used to decision tree construction. During we know decision tree implement a divide and conquer strategy for classification or for regression, and the tree construction process itself is a recursive procedure. Therefore, we need to specify the terminate the criteria to terminate the process. Here are some widely used criteria. For example, the first criterion is that the data set is pure. The second one is about the maximum tree depth. The third one is related to the minimum number of data points per leaf. And the last one is about information gain. In this session, we are going to define the term information gain. If we cannot produce sufficient information gain, the tree construction process should be stopped. There are several types of decision function. Some decision function take a single feature or a single attribute into consideration. In this case, the decision tree is considered univariate. On the other hand, if we simultaneously consider all attributes of an input data point, this is called a multivariate decision tree. In most of the cases, we use univariate decision tree because it is simple and it can be used to reduce the risk of overfitting. Okay, let's move our focus to measure the degree of impurity in a specific node. Here is the equation I specified last week. If we focus on one particular node M, one particular node in the decision tree node M, and MMK is used. MM is the data point reaching this node, and MMK is the number of data points belonging to class CK. So it is intuitive to define the probability of class K on this node M. Okay, PMK is the fraction of data point belonging to class K in this node. So it is MMK over MM. This is the definition. Please remember that there are two index. The subindex here is used to M is the index of the node, and the K is the index of class. Let's look at how to calculate the impurity of uncertainty for data point reaching node M. Actually, we call the list entropy. This is an important and widely used measure to multi-class classification. So IM is the entropy of node M. Here is its definition. As you can see, there is a sum operator over classes. So inside the sum operator, it is PMK log PMK. There's a negative sign here. In last week, we have specified some property of entropy. In general, large entropy means that data are more uniformly distributed over classes. In other words, it is not predictable because most classes have the same probability. So in this situation, the degree of uncertainty or the degree of impurity is high. Please remember this equation, the definition of entropy and its meaning. We are going to use this concept again. So let's specify some property of entropy. High entropy means that data are from a uniform-like distribution. So if you calculate a histogram over classes, it is a flat histogram. In this situation, it is less predictable because most classes have the same probability. You don't know which class is the most likely class for a given data point. On the other hand, we prefer to have a lower entropy. A lower entropy in this case indicate that data are from a varied distribution. There are a single peak or a few peak, and most of classes form the valleys. A histogram has many lows and highs. Values sampled from low entropy are more predictable. So we would like to have some split such that we can significantly reduce the amount of entropy. Okay. So once we have introduced the concept of entropy, the meaning of entropy, we are going to specify how to select the best split or how to construct the decision function for an internal node, for a decision node. Okay, so let's focus on one particular tree node. If this node is pure, it means that all data points reaching node M are of the same class. So in this situation, no further split is required. We can simply generate a leaf and stop the process. If node M is not pure, we need to split. We need to split the data set and continue the process recursively. Let's look at some notation when we need to have a further split of data in node M. As mentioned in the previous slide, we know MM is the number of data points belonging to node M. Since this is a decision, because this node is not pure, we need to further split the data set into several branches. So let's look at the situation for each branch J. We use MMJ to denote the number of data points go to branch J. And MMJK is the fraction. MMJK is the number of data point that goes to branch J and belong to class CK. So similarly, we can define PMJK, which is the fraction of data point belonging to class J and goes to branch J. So it is intuitive. It is simple. The fraction, it is a fractional number MMJK over MMJ. So let's look at the entropy after split. This is the key equation. So let's try to understand the meaning of this equation. It is a bit complicated, but it is interpretable. Let's focus on the first sum operator. Sum operator is over branches. So J is the index of branch, and they are total n branch for this node M. MMJ over MM, it is the fraction of data point goes to branch J. So in other words, this fractional number can be considered the importance or the weight of this branch J. So it is the weight of branch J according to the number of data point it belongs to, according to the number of data point it has. Let's look at the meaning of the second sum operator. It is over classes. So actually, this is the definition, together with the negative sign, it is the definition of entropy for branch J. So as you could see, we consider PMJK log PMJK. So it is the definition of entropy if you consider the second sum operator together with this negative sign. So after some arrangement, you can find that the entropy after split is simple. We can calculate the entropy for individual branch, and the entropy of each individual the entropy of each individual branch is associated with the weight. So it turns out that this is the entropy after split. I use this slide to summarize what I told in the previous slides. First of all, let's look at some particular decision node M. Before split, we calculate its entropy. I have specified the meaning of this equation. So it is the entropy before split. In the previous slide, we also talked about the entropy after split. They are M branches. So this is the value. This is the definition of entropy after split. It is a weighted combination of entropies of individual branches. So this term is used to indicate the entropy before split or the degree of impurity before split. And this term is the impurity after split. We want to minimize the impurity such that we can have a more reliable prediction. Based on this reason, we define a term Im subtracted by Im prime. So this is the entropy difference between before and after split. So this term is called information gain. We would like to have a split that can minimize the entropy after split or maximize the information gain. Okay, so actually we have several ways to develop our decision function, and a decision function can consider multi features or single feature, and there are a lot of thresholds. But we can choose the split that maximize the information gain. So this is the criterion this is the criterion of how to select the best split for each decision node. Okay, so let's specify how many split candidates And according to information gain, we can always choose the candidate with the maximum information gain. Okay, so for simplicity, let's consider a binary decision tree. Let's say for each decision node, data points are divided into two branches. The uh, and also we consider the univariate decision function because we look at a single feature or a single attribute xi. For a data point, we check the dimension I of this data point. If its value is larger than some particular threshold Wn, this data point goes to the first branch. Otherwise, this data point belongs to the second branch. Okay, so how many decision function candidate do we have? In this formulation, we know a decision function consider one particular feature I, one particular feature, and one particular threshold. So a split in this case is composed of a feature and a threshold. So my question is, how many decision function candidate do we have? So let's look at how many features we have. It is simple. If we are dealing with data point of dimension m, so there are m features because we consider univariate decision function. A decision node is constructed by using a single data dimension. So there are total m features. For each feature, we also need a real value threshold. So how many threshold do we have? Theoretically, we have infinite thresholds because it is a real value. However, just a few threshold value are representative. So how to determine the representative threshold? For decision node n, suppose there are m data point reach this node. So we have n values on each feature. So we can sort the n values. Okay. So in this way, we can control n minus 1 threshold value. The I threshold is the average of the i's and the I plus 1 sorted value. So in this way, let's consider one particular feature. Along this feature, we sort the data point according to the feature value. So this is a sorted list of L value. Actually, this is a real value. There are numerous thresholds, but there are just a few of them are representative. We can control we can sort the data values and control the corresponding threshold. There are m dimension and there are m minus 1 threshold. Totally, there are m multiplied by m minus 1 features, decision candidate, split candidates. We can estimate the information gain for each of the split candidate. So we can realize which one is the best, which one is associated with the maximum information gain. So this is the way we control a decision node. Once we know how to control a decision node, the process is repeated recursively until the process is terminated because we reach a leaf node. Okay, so we can realize how to control decision tree. I would like to use Chinese to refresh this part. 各位同学，那我这边呢用中文呢简短的叙述一下，我刚刚讲的这一个部分，那它并不算是太难了解所以你只要在这里面呢有一个关键的数学式，就是说我们知道一个 internal node，它在里面呢会有若干个资料，那我们怎么样衡量呢？说在这个点的时候呢，这些资料它的复杂度是多高呢？我们用这个词叫 entropy。那你可以想象说这个是资料的以类别来说它的乱度。那简单来讲呢，如果 entropy 越高的代表的意思呢，就乱度越高代表意思呢，就是说呢。这些资料的分布在不同 class 上面的分布几乎是几乎是 uniform 分布的。那这个是代表什么意思呢？这代表每一个 class 几乎都是有一样的几率发生。那某种程度上就是代表，就是说这个目前你在这个 node 你没有办法做一个有效的分类或有效的预测。因为呢，每一个类别发生的机会几乎是差不多高的，那在这种情况之下，你就没有办法好好的做预测了，你就会希望你再把这个资料呢再做一些区隔。那反过来讲呢，如果你的 entropy 的值比较低，那就代表呢只有少数一个或少数几个 class 它有比较高的几率。所以在这种情况之下，那你就比较可以预测了，至少你就预测那一个最高的或者是那少数几个最高的才是有可能的。那我们在做这个decision tree 的这个生长的，我们要建构一个 decision tree 的过程。那其实呢，就是要建构 leaf 或者是建构internal node。那建构 leaf 其实相对是比较简单的啦，就是说你已经在树叶这个地方了，就代表呢你这个资料呢已经够纯了在这个 entropy 的值呢都已经是那个entropy 的值都已经很低了或甚至它呢整个点都是纯的。那在这种都是同一个 class 的，那在这种情况之下，你就产生一个 leaf 就可以完成了。所以产生 leaf 这些东西并不难。所以难是难在于，就是说你在 internal node 你到底要选什么 split 才可以把这个资料呢它的这个乱度或者它的 entropy 呢可以继续把它给降低。所以呢我们要算就是在split 之前跟 split 之后的 entropy 的差距，我们才可以衡量这个 split 的好坏。所以在这个情况之下呢，我们就要来定义 impurity after split。那这个数学式就是定义，就是说，如果呢，你把这个资料呢根据这个 split 把它拆干成若干个 branch 的以后呢，它的 entropy 就是长得像这样子。那这个数学式看起来有点复杂，但是其实呢，你可以分析一下哈，如果呢，我们看第二个这个加总符号里面的这一串就包含第二个加总符号跟它里面的这一串。其实呢，这个看起来就是这个 branch J 它的 entropy 如果你把符号也搬进来的话，那的确呢，这一项呢就是呢 branch J 的 entropy。那我们再看第一个加总符号是什么意思这个加总符号呢，它的 index 是 J 也就是它的 branch，所以我们是考虑每一个 branch J 的 entropy。但是呢，我们不只考虑它的 entropy。我们前面呢还有算它的这个权重那这个权重它算的方式呢其实是很直觉的，就是说呢你在 个这些抵达了 dm 个 node 的这些资料点里面呢有多少比例它是属于到 branch J 的，所以简单来说呢这个 entropy after split 它就是这个每一个 branch 呢各自去算。每一个 branch J 它各自去算各自的 entropy 了以后再以加权的方式呢把它计算出来这个就是 entropy after split。那再来这一页就是关键我们说 IM
是以 DM 个 decision node 来看，它在还没有展开之前，它的 entropy 它的乱度。那这一个呢 ，IM prime 呢，根据刚刚的定义，就是呢，它是在 split 以后呢，资料分成很多个 branch 了以后呢，再算它各自的这个在 split 以后呢，它的 entropy 它的乱度。所以你当然很希望呢，就是呢，它的这个乱度呢，可以降得越低越好哦，代表呢，在每一个 branch 我都很好做分类。所以为了达到这个事情呢，我们就看这两者之间的差距哦。那这两者之间的差距，也就是这个 split 的功效了，因为它把乱度从 IM 呢，改变成 IM prime，所以来说呢，这个什么叫做资讯量的提升呢 ？information gain 呢，其实就是乱度的下降的意思啊。那就是 IM 呢减掉 IM prime，就是代表这个乱度呢，下降了多少？从原先的地方到更新后的地方，那所以这个之间的差距就是叫做 information gain。好，那所以呢，这边的来说呢，就是说，如果我有一个 split，我就可以去算它的 information gain 是多少。那如果我有很多个 split 的话，那我就可以算它各自的 information gain，然后挑一个split，它有最好的、最大的这个 information gain。那这边呢，这页投影片主要就是去讲说，那我们到底会有多少个 split，在 implement 上面，这个大家写作业的时候有可能会用到。那简单来说呢，就是我们现在都是考虑这种一个 decision node，一个 decision function，它只考虑一个decision 一个 feature 或一个 attribute 的情况，所以呢，它这个一个 split 通常就是考虑一个特定的 feature。跟考虑一个特定的一个阀值一个 threshold。那总共我们会有几个 feature 呢？假如说我们处理的资料的维度它是 m 维的话，那所以呢，这一个它的 feature 的数量就有 m 个。然后呢，我有多少个 threshold？因为你在某一个维度上面是 real value 的，所以理论上来讲，它会有无限多个实数值，它有无限多个 threshold。但是实际上呢，你会对于这个分类的结果会造成不一样的影响的时候呢，其实并没有那么多个。那我们来看怎么说的假如说总共有 n 笔资料抵达了这个 DM 个 decision node。那如果我今天呢要选择的是某一个维度的 feature，所以呢，这 n 笔资料在那个 feature 上面都会有一个值嘛，都有一个 feature value，所以它总共会有 n 个 feature value。那我在这个值上面呢，去把它做 sorting，从值小一直排到值大。那你的 threshold 呢，只有切在这个点跟点，资料点跟资料点之间才会有差距。所以在这个情况之下呢，只有 n 减一个 threshold 就具有代表性。那其中 di 一个 threshold 呢，就是 di 一个点和 di 加一个点，它们 sorting 好的呢，这个资料点的它的 di 一个点跟 di 加一个点，它的平均值。OK，所以这个就是总共你有 m 个 dimension，你有 n 减一，每一个 dimension 有 n 减一个 threshold。所以呢，你总共有几个 candidate 呢？你总共有几个 split candidate 呢？就是 m 再乘上 n 减一。那每一个呢，都可以去算，这个 information gain 是多少。所以我就可以从这些 candidate 里面，去挑一个最好的 split。所谓的最好的是以 entropy 的方式来衡量的最好的。那我这边呢，就讲完了这个 decision tree 它是怎么建构的啊？因为我们说嘛，decision tree 就只有 leaf 跟internal 的 node 只有那个 leaf 跟这个 decision node。那 leaf 很简单就是你够纯了或 entropy 够小了，你就产生一个 leaf node。那一个 decision node 就是根据 information gain 来产生。那因为整个 process 都是 recursively 去呼叫的，所以呢反正到最终呢就只有两个就是说你只要去管就是这个 decision node 跟这个 leaf node 怎么建，那我们这边都讲过它是怎么建构的。OK，so Here is the algorithm to summarize what I told about a decision tree. So this is the function used generate tree. This is the function used to control a decision tree. So first of all, let's check if we can create a leaf node for the current data set. So we estimate the degree of impurity in terms of entropy. So if the data set, the entropy of this data set is less than some particular threshold, we consider the data are pure enough, they are predictable. In this case, we can create a leaf node with its label as the majority class in this data set. Okay, this is the situation to construct a leaf node. Otherwise, this node is a decision node. In this situation, we call a function split attribute. This split attribute function is used to select some particular attribute or is used to identify the optimal split so that with this split, we can divide the data into several branches. For each branch, we recursively call the generate tree. Okay, so the focus is how to use information gain or entropy to control this function, split attribute. I listed the function of split attribute here. Okay, our goal is to identify a split with the maximum information gain. Okay, so suppose a data point lie in a d-dimensional space. They are d features or d attributes. So let's consider there is a for loop here over attributes. For each attribute, we need to consider one particular threshold, or we can calculate its entropy. There is a if-else instruction here. It is used to indicate attribute I is a categorical or real value attribute. If xi is a categorical attribute, so it is discrete with n values. So we don't need to have additional threshold function because it is categorical. Each data point has some discrete state according to attribute I. So according to this attribute, the data set can be divided into m subset because m is the number of the the number of states, discrete states of this categorical variable. Okay, so we can calculate the split after we can calculate the entropy after split. This function here, this line here, is used to maintain a data structure or a variable. It is used to indicate the currently best split. This part is used for categorical attribute. On the other hand, if we are dealing with a data set with a real value attribute, in this situation, we need to consider several possible thresholds, as mentioned in previously. So, according to the threshold, the data set can be divided into two subsets. For these two subsets, we can calculate the entropy. Similarly, we use line 11 to maintain the best split currently. So after running the for loop here, we can determine the best attribute with the highest information gain. So with split attribute and the generate tree function, we can use them to construct a decision tree recursively. Okay, let's look at some property or limitation of a single decision tree. We measure the complexity of a decision tree by the number of nodes in this decision tree. Okay, so let's look at this figure. The x-axis is used to indicate the size of a decision tree in terms of the number of nodes. And the y-axis is used to indicate the accuracy. We know tree reconstruction is a recursive process. Along this process, we iteratively increase the size of the decision tree. So there are two learning curves in this figure. The solid line is used to indicate the learning curve of the training data. The dashed line is used for the curve of testing data. So let's look at the training curve. According to this solid line, as you could see, along the training process, the performance increased. Okay, so in terms of training data, we prefer to have a large decision tree because we can boost the training accuracy. On the other hand, as you could see, the curve of the learning curve of the testing data, you might find that after selecting the first 20 nodes, after this threshold, the performance decrease when we construct a larger decision tree. In this situation, in this case, where the performance gap between training and the testing is large, we consider overfitting over the risk. The phenomena of overfitting occurs. So according to this figure, this figure specifies an important limitation of decision tree. A decision tree tends to overfit, especially you have a large decision tree. How to address this problem? We need to control the size of the decision tree. So here are some practical strategies to control the size of a decision tree. For example, you can fix the depth, the tree depth, or you can specify the minimum number of data points per leaf. Once we don't have sufficient data in the node, the split process should be stopped. And the third criterion is about information gain. Once we cannot sufficiently increase information gain, the process of split should be terminated. The fourth strategy is called tree pruning. Once we grow the huge tree, we can apply some heuristic rule to reduce the size of a decision tree. Here are some widely used strategies to control the size of decision tree. In practice, we can use the combination of these four strategies. Okay, in the following, I'm going to specify two powerful ensemble methods to address this problem. We can combine several small size decision tree and boost their performance. One algorithm is called bagging, the other is called random forest. Both of them can improve the performance of a single decision tree. Also, they make a decision tree more robust to noisy data, and they can be used to reduce the risk of overfitting of decision tree. So our focus will be bagging and random forest in the next section. Okay, let me summarize what I told about decision tree. Decision tree are one of the most popular machine learning and pattern recognition tool. They are easy to understand, implement, and use. Also, they are computationally cheap because we use greedy strategy for training, and during testing, we feed the data point to the root, and the inference process goes from the root to one particular leaf node. Information gain is widely used to select the useful attribute or feature during tree construction. In the literature, a Gini index is also widely used. It is another criterion, but the idea of information gain and the Gini index are similar. In this lecture, we talk about information gain. If you are interested in Gini index, you can check Wikipedia. And that a decision tree can be used for not only for classification, decision tree can be used for regression and the density estimation. You just use some criterion to estimate the purity of regression, and you can use a constant for each leaf node. Okay, it is about decision tree. Do you have any question? 这堂课我主要是把 decision tree 讲完了哈。那一些回顾就写在这一页投影片，不晓得大家。
老师可以问问题吗？
可以，请说。
对，老师想问一下，就是说，所以那个决定 attribute 那边的话，其实看起来看那个 code 是不是其实一个 node 就是运用一个 attribute 而已，还是它其实可以由一个 node 可以由复数个 attribute 去决定？
一个 node 可以只考虑一个 attribute 这也是我们这堂课或者是这个演算法就是刚刚我们贴的那个 pseudo code 里面用 implement 的是这个 univariate 的这个 decision node， 一次呢只考虑一个 attribute。那实际上呢在一些比较复杂的 implement 的机制里面，你一个 decision node 也可以使用多个或甚至全部的 attribute， 这些是考虑的哈。但是我们这边讲简单的就好，就是呢这个我们通常都是使用一个 attribute， 而且事实上呢使用一个 attribute 的效果在大部分情况之下效果甚至更好，因为呢它比较简单，它比较不会 overfit。你用了多个 attribute 的话，会加快它的 overfit 的趋势这样。
了解，那想再问一下，就是说在实作上会有避免同样的 attribute 被重复使用吗？
通常是不需要做这件事情的你可以了解得到，就是说呢，这个选择的过程是根据 information gain。如果呢，它靠同一个 attribute 可以制造的很大的 information gain，那就选它也没有关系。不过呢，通常这个事情比较少发生，因为当你的上面的比较早期的这个点已经选到某一个特征了，它已经把这个性质考虑进去，至少它分成两个 subtree 的时候，是以这个 attribute 来分类的。那所以呢，到某一个左指数跟右指数的这两个地方呢，至少在这个 attribute 上面可能没有更多的资讯可以供他们使用了，所以一般来说也比较少选择到。但是呢，我们并没有去用你刚刚说的这个策略啦，就是说防止它选到一样，因为如果选到一样，就代表它其实已经没有更好的选择了。这样子，以 information gain 的角度来看。
了解，谢谢。
客气。还有没有其他的问题有关 decision tree？ 如果没有的话，我们休息10分钟哈，到11:15哈。Let's have a 10-minute break. Hello everyone. Let's get started. Okay. In the previous section, we talked about decision tree. In this section, I'm going to specify two famous ensemble algorithms called bagging and random forests. Uh, the two ensemble methods can combine multiple decision tree and improve the performance of a single decision tree. First of all, let's consider bagging. Bagging is the abbreviation of bootstrapped aggregation. Bootstrapped aggregation. I'm going to specify the meaning of bootstrapping later. This algorithm was invented by a famous researcher, Leo Breiman, in year 1994. Bagging is a method for generating multiple versions of a predictor and use those predictors to get an aggregated prediction. Okay, so here are some keywords. Here a predictor, you can consider a decision tree is a predictor or a machine learning model as a predictor. So let's try to control multiple different versions of a predictor. We can control multiple decision tree. These decision trees are different from each other. So we can combine them, combine this decision tree to get an aggregated predictor, a merged decision tree. The aggregation average the versions for regression and thus a majority vote for classification. We know a decision tree are developed for either regression or classification. For regression problem, if there are multiple decision tree, so how to compute the output for individual input data point? We feed this data point to multiple decision tree. We will get a multiple regression value, one value from a single decision tree. We simply average the output value to get the final prediction. For a classification problem, we do the same process. We feed this data point to all the decision tree, and each decision tree will vote for one particular class. Finally, this data point is predicted as the class of majority vote. Okay, so this is the operation of bagging once we get multiple versions of decision trees. However, how to generate multiple different and even complementary decision tree? So bagging implement a specific technique called the bootstrap sampling. Given the training set D containing n training data points, we can create another data set D prime by drawing an example and at random with replacement from D. So I'm going to use an example to illustrate the meaning of this sentence. According to this sentence, we know that we are given a data set. We want to create another data set of the same size from D data set D to a generated data set D prime of the same size N. And how to create this additional data set? We use sampling with replacement. This is this process. So I would like to use an example to illustrate the process of sampling with replacement. Sampling with replacement. Okay, let's consider an example. Here is a data set of 10 training data. They are 10 training data. We would like to create another data set of 10 training data. So how to carry out this goal by using sampling with replacement. First of all, since there are 10 training data, there are 10 training data, we randomly sample one particular training data. In this case, we sample training data point number 7. So we put this training data here. So this is the process of sampling. However, what we implement is sampling with replacement. So we put this data point back to the original data set. When we want to sample the second data point, we also sample this data point from the 10 candidates. So in this process, we sample training data number 8. The process is repeated until we have 10 training data. So this is the first row is D, the original training data set. And the second row is D1. D1 also has 10 training data. However, as you could see here, there is redundance. For example, we have 2 copies of training data number 8. We have 3 copies of training data number 10. So this is another data set D1, but with different let me rephrase it. D1 is of the same size as D, but D1 is different from D. So this is the process called sampling with replacement. And the process can be repeated several times. In this case, we repeat the process 3 times. So we have 3 different versions of D prime. Okay, so this is the simple process. This is the simple process of bagging. If we want to combine capital D decision tree, we use this process. We run this process T times, so such that we will have D1, D2 to D capital T. Okay, so we have capital T different data sets. We train a decision tree or some distinct classifier on each of the generated data set. We have decision tree T for data set DT. Once we repeat the process for each of the bootstrapped data set, so we will have T decision tree. How to carry out classification on a new data instance? Actually, it is carried out by using majority vote. Okay, so this is the process of bagging. Here is the flow chart. Originally, we have given a data set for supervised training. In the first step, suppose we want to generate a T decision tree. So we implement sampling with replacement technique such that we will have T copies of the data set, and all the data sets are different from each other. In previous session, we talked about how to construct a decision tree from a given data set. So we can construct a decision tree C1 based on the data set D1. Similarly, we have a C2, a decision tree C2 for the data set D2. the process is repeated until that we will have a T decision tree. Okay, this is how to get the multiple versions of a decision tree. During testing, we can combine a list generated decision tree by majority vote. Okay, so this is the training and the testing flow chart. Look at the example to illustrate the power of bagging. Let's look at the classification problem, two-class classification problem in a two-dimensional space. As you can see, this is a two-class classification this is a two-class classification problem, and the ground truth boundary is an ellipse. So this is a nonlinear decision boundary. If we use a decision tree, univariate decision tree, it is difficult to get a satisfactory result. Here is the result if we use a single decision tree. In the paper of bagging, Professor Leo Bremen used cut as the decision tree. This is a specific category of a decision tree. Cut is very famous because it can be used for classification and regression. We use cut to control the decision boundary. The black ellipse is the ground truth boundary, but the decision boundary, the decision region red and the decision region blue is used to indicate the decision boundary generated by this decision tree. Okay, so as you can see, the contour of the boundary is different from the ground truth boundary of this ellipse. Once we use bagging, we can control 100 copies of the data bootstrapped data set, such that we will have 100 corresponding cards. Okay, so in the paper, they are called the 100 bagged cards. Here is the decision boundary. As you can see, this is the majority vote, so we can estimate the confidence. So as you can see, the region of the red region and the blue region more consistent with the ground truth boundary, as you could check. Here is the decision boundary of a single cut, 100 cut by using bagging. So by using bagging, we can better approximate the real decision boundary. In the following, let's look at some evaluation for bagging. In the paper of bagging, Leo Bremen conducted experiment on some benchmark data set. Here are 7 benchmark data set, and each day there are 3 currents here. They are used to indicate the number of training data, the number of feature, attribute, or variable, and the number of data classes. Okay, so we are going to compare a single card and the 50 bagged card. For each of the 7 data set, the error rate by using a single decision tree and the error rate of the bagged classifier are reported. As you could see here, take waveform dataset waveform as the example. If we use a single decision tree, the error rate is more than 28%. But if you use a 50 bagged card by using bagging algorithm, we can reduce the error rate from 29 to 19. So the improvement is significant. So we can calculate the relative decrease in the error rate. So 34% is quite significant. Okay, similar observation can be found in the other 6 data set. The relative improvement is very significant. This table illustrates the power of bagging. Actually, bagging is simple to implement. Do you have any question about bagging? 因为 bagging 的演算法比较简单，那我们刚刚就讲完了这个 bagging 怎么样用 bagging， 然后来结合多个 decision tree。那大家对 bagging 有没有什么问题？ Okay, since there is no further question, let's talk about random forest. Actually, random forest is widely used algorithm, and the random forest in most cases perform better than bagging. So let's look at the detail of random forests. Like bagging, random forests were invented by the same author, Professor Leo Bremen, and the random forest was proposed in year 2001. A random forest is an ensemble method specifically designed for decision tree classifier. So this is the reason why this method is called random forest, because it is composed of several decision trees. Okay, so this is the meaning of forest. Let's look at the meaning of random. Random is the key feature of this machine learning methodology. Random forests introduce 2 sources of randomness. The first randomness comes from data. The process is the same as bagging. In bagging, we implement bootstrapped sampling. It is sampling with replacement to construct multiple copies of a data set. So this is the randomness from data. The other source of randomness comes from the input feature vector. Okay, so let's look at the detail of the 2 sources of randomness. For data randomness or bagging, each decision tree is constructed by using a bootstrapped data set. So it is used to ensure that all the decision trees are different because they are constructed from different bootstrapped data sets. The second randomness is called the random vector. Please recall that in decision tree, we say a decision node is associated with a decision function. And this decision function select some particular split. We select the best split. This best split, the best split is the one with maximum information gain or other criteria Gini index. We search all possible split candidate. So this is what we do for decision tree. However, in random forest, we don't consider all attribute or all features. Actually, we randomly select a small subset of the feature. So, for example, there are 100 features for input data point. If we set the value of m to 5, we randomly, for each decision node, we randomly select 5 attributes out of 100 attributes. So in this decision node, the best split is selected from the 5 attributes. Okay, this randomness increase the diversity among the decision node Also, they increase the diversity of all the constructed decision tree. Okay, please remember the two sources of randomness. In the following, I'm going to use a figure to summarize the property of random forest. Given a data set D as the input, similar to bagging, we use bootstrapped sampling or sampling with replacement. We can construct T bootstrapped data set from D1, D2 to DT. Okay, so in this part, the process is exactly the same as bagging. However, given a data set as input, we introduce the second source of randomness. Here we construct a decision tree T1 for data set D1. In each decision node, decision node, and decision node. In each decision node, we randomly select a small subset of attribute. According to the selected attribute, we can choose the attribute with the maximum information gain to construct the tree. Please notice that for each of the decision node, it has its own randomly selected attribute. So the behavior of decision node are different from each other. By using the second source of randomness, we increase the diversity of decision node inside this decision tree. The same random process is applied to each of the decision tree. So as you could see, the diversity among the constructed decision tree is increased. This is an important property. Theoretically, for an ensemble measure, we want to construct powerful individual model. We also want to increase the degree of complementary to each other. Okay, so this is the process of random forest. After generating a T decision tree, we still use majority vote to carry out final classification or regression. Let's look at how to implement a decision node for random forest. Actually, there are many variants of random forest in the literature. In this slide, I specify three popular methods to construct a decision tree in random forest. However, in the following, I will use a method one to construct the decision tree. Okay, so we use capital M to denote data dimension. This is for each data point, it has m dimension. It is represented by a m-dimensional vector. Okay, so m is the number of feature or number of attributes. Here, let's consider another notation, lowercase m. Lowercase m is less than capital M, so it is a constant. We also consider another constant, L. The value of L is less than M. Okay, so let's consider the first method used to implement the second source of randomness in random forest. How to generate the randomness from data dimension. Since capital M is the number of data, capital M is data dimension, we choose M attributes randomly and from capital M dimension, and compute layer information gain. Finally, we choose the attribute with the largest information gain to split the data set. This is one of the widely used strategy to control random forest. Okay. Now let's consider the second method. When M, this method is popular when the value of M is small. Okay. So in this situation, we randomly select L of the attribute, L attribute from M. Then we compute a linear combination of the L attributes using weight generated from -1 and the +1 randomly. So suppose there are 20 dimensions of the data dimension is 20. We can randomly select 10 dimensions. Then we linearly combine the 10 selected dimension with 10 randomly selected weight. Okay, so we project after this process, we project data to a new dimension. In this case, we just have one-dimensional data. In this situation, we try to get a threshold. In this case, we don't need to consider information gain because we just have a single choice about feature. We just use information gain to determine the optimal threshold. This is method number 2. Let's consider method number 3. We compute the information gain of M attributes. And we sort the information gain and select the top M attribute according to layer information gain. In this situation, we have M choice. We randomly select one of them to construct the split. Okay, so this is there are several ways to implement random forest. In this slide, I summarize 3 popular choices. In the following, I'm going to use method number 1 to construct a random forest. 不晓得大家对这一页有没有听懂哈？简单来说，这个 random forest 的前一半呢，就跟 baking 做的事情是一样的。就是说我有一个 data set， 那我产生多个 data set， 那这个 data set 呢，它长得不一样，所以长出来的 decision tree 就是不一样的。那在 random forest 其实它的成功呢，主要是来自于第二个形态的这个 randomness， 也就是说呢，它的这个每一个 decision node， 这个每一个 decision node， 它并不是考虑所有的 attribute。它只考虑 random 选择一些 attribute 来考虑。那每一个 node 呢，它 random 选择的东西是不太一样的。那大家可能乍听之下会觉得说，我原先的选择的范围比较大，是所有的 attribute 里面去挑最好的。那我现在呢，我只 random 从这么大的search的 space 里面挑一个小的集合出来，从这里面去挑的比较好。从一个里面挑一个比较好的，那这样子是不是限制呢？它的这个 power 呢？的确哈，如果你以单独一个 node 来看，或者是以单独的一颗 tree 来看，这样子想是没错的。可是呢，我们在 ensemble 的 method 里面哈，我虽然没有去讲一些证明，可是呢，有一些理论的基础呢，就是说一个 ensemble model 的成功呢，它主要来自于2个重要的 factor。一个呢是这些 individual 的 model 或 individual 的 weak learner， 它本身自己要很强大。 那第二个呢，就是呢，它呢这些 weak learner 或这些 decision tree 之间彼此之间要互补。所谓的互补，就是要让他们不是那么的像，每个都蛮强的，可是他们又不是那么的像。那光这件事情呢，我们刚刚所说的这个 random 去选一个 subset 出来，就是在增加它的 diversity，因为每一个点选到的 subset 是不一样的。然后呢，每一颗 tree 呢选到的这些 attribute 每一次都 random，每一个 decision node 都 random 一次，所以呢，大家的行为都不太一样，所以呢，它会增加它的这个就是它的 diversity。简单来说呢，我就是稍微损失一颗 tree 的这个它的 power，但是我大幅度的增加不同 tree 之间的这些互补性。那整体来说empirical 上面来讲，random forest 是一个相当成功的一个演算法。那我们这边在这一页投影片主要是说，我们刚刚非常的 high level 去说我每一个 node 要从一些 random 的一些 feature，random 选择的一些 feature 里面去选好的 split。那实际上怎么 implement 呢？其实大家如果去看文献，甚至是网络资料，有各式各样不同的 implement 的方式。那有一些呢，还跟这个 application 的 domain knowledge 是有关的。那我们这边讲的是PR 是要讲一个比较 general 的一个课程不见得跟某一个特定的 application 有关。所以在这边呢，我选择列出来的就是一些一般来说比较常用的这些 implement 的方式，而且并没有用到不同的 application、不同的 domain 的 knowledge。那我们这边讲就是说，假设资料是在一个大 M 维的空间，那如果我要 implement random forest 的这个这个每一个 decision node，我可能要么会需要一个小 n 一个额外的值根，或者是一个大 L。那这两个东西呢都是小于等于大 N 这样子，尤其是小 n，通常呢它的值呢会远小于这个大 M 这样。那 Master One 怎么做的呢？就是说当你在某一个decision node 的时候，我原来呢在 decision tree 我总共有大 M 的 attribute 可以选，那现在呢我就不要，我从大 M 的 feature attribute 里面呢，我先 random 挑 M 出来，那所以我的摄取的范围就从大 M 变成小 M。那从这里面呢，小 M 的自己的 attribute 要去选各自最合适的 threshold，看看到底哪一个的 information gain 最大我就是选择这一个来展开这个 data set， 再展开这个来用它这个 split 来针对于这个目前的这个 decision node。那我这边必须得强调一颗 tree 里面有不同的 decision node， 这个 random 的 process 是每一个 node 大家都不一样不然到最后大家都选择一样的，都是选择同一个小 m 尾的 attribute， 这是不是的是每一个 node 呢，它选到的 attribute 呢都是不一样，因为每一个 node 它有各自 random 值。那第二个策略也算是常用那这个策略处理的问题就是大 M 这个值本身就已经不高了。这个我们在处理这个低维度的资料的时候，那在这个时候呢，我们可以呢，就是从这个大 M 维里面呢，去 random 挑大 L 维出来例如说，从原先的20维资料里面 random 的挑10维出来，那这是第一层次的 random。那第二层次的 random 就是说呢，这 L 维呢，我要去选择一个 weight 一个 weight。总共有10个大 L 如果是10维的话，总共我们就选10个 weight。那这个 weight 的值，每一个 weight 的值都是 random 挑的，那它的值域是介在正负1之间，所以呢我就可以把这大 L 维这10维呢，把它压缩成1维压缩成1维，因为呢我们就使用这种 weighted combination 这样子。好，那现在呢，在这个情况之下呢，资料都已经压缩在一个1维的空间了。那这个时候我们就去找一个最好的 threshold， 所谓的最好的 threshold 就是可以把 information gain 提高最多的。那这是第二个策略那第二个策略呢，主要是应用在这个 M 的选择并不多的时候。那第三个呢，第三个也算是常用那就是说呢。总共有大 M 维的 attribute， 那我们可以为每一个 attribute 去算它的 information gain。那总共呢，我们把最好的就是 information gain 最大的小 m 个 attribute 都挑出来。那这个时候呢，我们就不是选最好的那一个，不是选 information gain 最高那个，而是从这里面呢，从小 m 个最好的 attribute 里面 random 挑一个就这样子。所以这边呢，就是3种不同的来执行这个 random forest 用来建构一个 decision node 的一个方式。那其他的呢，就跟 bagging 跟 decision tree 都是一样的。Okay, in this slide, I use a algorithm to summarize. I use this slide to summarize the algorithm for random forest. Especially this forest is constructed by using method number 1. Okay, suppose we want to construct capital B decision tree. So there is a for loop here. In this for loop, there are 2 steps. Step A is to construct a bootstrapped dataset DB of the same size from the original dataset. So this dataset, bootstrapped dataset DB, is used to construct the decision tree. So we want to grow our decision tree TB based on the bootstrapped dataset DB by recursively repeating the following step for each of the decision node until reaching a leaf. Because we implement method number 1, so for each decision node, we randomly select m attributes from the capital M attributes. We pick the best attribute and its threshold as the split. In this situation, we can use the threshold to divide the data set into 2 branches. So we can split the node into 2 daughter nodes or 2 branches. Okay, so the process is repeated until we get the capital B decision trees. So finally, the output of random forest is a set of decision tree. It is the collection of TB for B ranges from 1 to capital B. Given a testing point or testing data point X, we feed this data point to all the decision trees and use the majority vote as the classification result. Okay, so this is the process of random forest. Let's look at some performance comparison among bagging, random forest, and ADA boost. In the paper of random forest, Professor Leo Bremen considered 20 benchmark data set. The first 13 data set from UCI, this is a collection of several benchmark data set. And for each data set, 90% of training, 90% data are used for training. The rest are used for testing. Okay, so there are 13 data set from UCI, and the last 3 set are large. Okay, and the last 4 sub data set are synthetic. Okay, here the last 4 data set are synthetic. Okay, so in this table, we also summarize the size of training data, the size of testing data, the number of attributes of number of features, and the number of data classes. Okay, in the first 13 data set, they are from UCI. So we randomly select 90% of the data as training, and 10% of them are used for testing. Let's analyze the result. let's look at some comparing method. The baseline method is a single decision tree. This is the baseline learner. We just have a single decision tree. Okay, let's look at some variant of random forest. The first variant is called forest I. It is a single input version. Let's look at the details. We also use a method 1, and by setting the value of m to 1 for the decision node construction. This is an extreme case. In each decision node, we randomly select a single attribute. Based on this attribute, this selected attribute, we can divide a node into 2 branches. So this is the extreme case. M is equal to 1. In this process, we can use random forest to generate 100 decision tree for all the data set, except 200 tree for data set zip code. Let's look at the data set table. Zip code is a bit complicated, so we can boost the performance by having more decision tree. So this is the reason why Leo Bremen increased the number of decision tree for this particular data set. For the other 19 data set, 100 decision tree are sufficient. This is a variant of random forest called forest I. Let's look at the other variant. This variant is called selection. Just like the first variant, we use method number 1 to control the decision node. In this case, let's consider 2 choices of the value of m. The first one is to set the value of m to 1. And the second choice of m is set to log of m plus 1. Okay, m is the number of data dimension. Okay, so based on the 2 different values, we can construct 2 decision tree according to a single bootstrapped data set. Which one is better? In this situation, the author, Leo Bremen, proposed to use out of bag arrow to select which value is better for this particular bootstrapped data set. How to calculate out of bag arrow? Please recall that we use a bootstrapping strategy to generate a new data set. So due to the redundancy, one particular data point may appear several times in the bootstrapped data set. In other words, some data point in the original data set do not appear in the bootstrapped data set. So they can serve as the validation data set to determine which value is better for this particular bootstrapped data set. Okay, so this is the code selection. We want to compare the performance of random forest with AWS. So in the implementation, AWS is used to combine 50 decision tree, except 100 decision tree in the data set lib code. 我这边用中文讲一次这一个点哈，那这个可能用英文讲，不晓得大家有没有听懂？就是说呢，这个是一个 implementation 的 trick， 就是说我们在 implement method 1的时候，我们要事先决定 m 的值是多少，那不同的 m 的值可能会有不同的效果。那在这一个设定之下，这个作者呢，他是考虑2个不同的 m 的值，一个 m 的值是设的很小，就最极端的 case， 每次只考虑一个feature，而且这个 feature 是 random 选的。那第二个选择呢是 log m 加一哦，就是你看你有多少维度，再加一维，然后再取 log 啊。那这是第二种选择。那这两种选择哪一个比较好？我们要怎么衡量呢？那这边呢，它是用这个所谓的 out of bag error 来衡量的。那什么是 out of bag error？我们知道 random forest 它也跟bagging 一样，是使用这个 bootstrap 的这个方法，去产生多个 dataset copy 不同 dataset version。那我们知道它是这种 sampling with replacement 哦，就是你 sample 完了以后，你会放回去，所以它下一次还是有机会会被 sample 到。所以在这个过程里面呢，你可以发现哦，有些 data point 它被 sample 了很多次，那有些 data point 在这个 data set 里面它就不出现了。那不出现有没有什么好处呢？不出现，它这边就要善用这个好处，因为你既然不出现，所以呢，你在建造这棵树的过程里面呢，你就不会用到这个没出现的。那这个没出现的呢，某种程度上就可以当成是 validation 的 data set。那我就用这个我所选到的这些 data 去长一棵m 等1的时候的树，那还有 m 等于这个 log m 加1的时候的树。那这两棵树哪一个比较好呢？我就把这个 bootstrap dataset 没有用到的、没有挑到的那些 data， 那些 validation data 丢进去这棵树，跟丢进去这棵树，那它总是会有一棵比较好的，那我就选到了。那这是对于某一个特定的 bootstrap 的 dataset。那下一棵树，这个 process 又重新跑了，然后下一棵树的这个 out of bag 的这些 validation 的 data 又长得不一样。所以在这种情况之下呢，我每一个 bootstrap 的 dataset 我都一次长2棵树，那从里面挑一棵比较好的留下来。OK， 那这个就是它的选择的过程 selection。So let's look at the performance comparison among 4 methods. The first one is a single decision tree. And the second and the third one are the 2 variants of random forest, including forest RI and the selection variant of random forest. The last method is ADA boost. Okay, so in this table, we report testing set errors in percentage. So as you could see, a single decision tree produce a high error rate in the 20 data set. Once we use a random forest RI variant, we can significantly reduce the test error rate. Okay, so as you could see, this is a significant improvement if we use random forest. Now let's compare selection variant and the forest RI variant. As you could see, our selection variant is a bit more complicated, and it is used out of bag validation strategy to choose a beta value of m. So in most cases, as you could see, in most cases, the testing error can be further reduced. Finally, we compare the performance of ADA boost and the random forest. In this paper, ADA boost, random forest is slightly better than ADA boost. So this is the result this is the experiment conducted by Leo Bremen. So actually, ADA boost and the random forest are widely used in the literature. Random forest is simple to implement, but ADA boost can select fewer weak learners to have comparable performance. So you can use both of them in your application. Okay, finally, the content are not from the content of this lecture is not from our textbook. Instead, the content of this lecture come from several papers, including this is the AWS paper, decision tree bagging, and random forest. You can check the detail by study these papers. Do you have any question about decision tree and ensemble models? 大家对于刚刚讲的这个 decision tree、AWS、bagging 或 random forest 有没有什么问题呢？ Okay, if there's no question, let's have a 10-minute break. Hey, hello. Let's get started. Um, Previously, we talked about ensemble methods. Ensemble method is simple and practical. In most of the cases, ensemble method achieve much better performance than the base predictor. In this section, let's talk about another family of machine learning methodology. They are called kernel methods or kernel machines. Actually, kernel method is one of the best machine learning methodology in the literature, especially before the era of deep learning. In many applications, kernel method achieve the best performance. Kernel methods is also a family of machine learning methodology. So in the following, let's talk about the features of kernel method, and one I will focus on one particular kernel method member. It is support vector machines. Here is the outline of the lecture kernel methods. It is divided into 4 parts. In the first 2 parts, let's consider the 2 main features of kernel methods. The first feature is dual representation. That is, kernel methods work on the dual representation of the model instead of the primer representation. We work on a dual representation. In dual representation, we consider the relationship among pairwise training data. For each pair of data, we want to estimate its similarity. In this case, we control a kernel function or a kernel matrix to summarize the pairwise relationship among the training data. So here are 2 main features of kernel method. Actually, there are a lot of methods belonging to kernel methods, such as support vector machine, Gaussian processes, kernel PCA, or kernel FLD. Due to the time limitation, I will focus on one particular algorithm called the support vector machine, or SVM for short. Actually, SVM is in most cases, SVM is the best method in the family of kernel methods. And the support vector machine has its own theoretical support. It can be applied to classification, regression. We are going to specify its application to classification and regression. However, support vector machine can be utilized for density estimation, one-class classification, but I'm not going to specify the application other than classification and the regression due to the time limitation. Okay, so in the beginning, let's look at the meaning of dual representation. We want to deal with the dual representation of a classification or regression problem. Before talking about dual representation, let's talk about parametric or non-parametric machine learning models. Actually, most machine learning or pattern recognition methodology can be divided into parametric or non-parametric model. Let's look at the meaning. Actually, in the previous lectures, we have talked about some example of parametric model and the non-parametric model. Let's look at the definition of parametric method. That is, we learn a model. After training, the training data can be thrown away. We just learn the model, and the learned model is sufficient to carry out the underlying task, such as classification or regression. This method of this category is called a parametric method. An example is the linear model for regression. We use a Y to denote the model. Given X as the input, the linear regression is parametricalized by W. After training, we can determine the optimal value of W. In this situation, after training, we can determine we get the optimal value of W, and we don't need to have training data during testing. For each testing data, we feed this testing data into the model. We will get the result. For such a model, we say this is a parametric method because this model is fully parametricalized by the learnable parameter W. And we don't need to have the training data after training. Let's look at another example. Let's look at another category, non-parametric method. Compared with parametric method, training data are required even after training. In homework number 2, we use nearest neighbor classifier to carry out classification for data point projected in a low dimensional space by using Fisher linear discriminant. You use a nearest neighbor ruler to carry out classification. In other words, you need to keep the original training data even after training. So this is called a non-parametric method. Training data are required. Separate vector machine or other kernel method belong to non-parametric method. Some or even all the training data are required even after model training. Kernel methods have several members, including support vector machine, Gaussian processes, or kernel PCA. The main feature of kernel method can be specified by using this sentence in red. Let's look at the meaning of this sentence. A prediction of kernel method are based on linear combination of a kernel function evaluated at the training data points. I believe if you are a beginner of machine learning, I guess most of you feel confused about this statement. But in the following lecture, we are going to talk about this statement formally and in detail. Let's look at some keyword. A kernel function. Actually, this is the key feature of kernel methods. We need to select or learn a kernel function. This kernel function is applied to a pair of data. The pair of data, one from training and one from testing during the testing phase. So this is the meaning of a kernel function evaluated at training data point. This is also the reason why kernel methods are non-parametric methods, because training data are kept even after training. So if we evaluate the kernel function at several training data point, we will get multiple output, one output from one particular training data point. So the prediction is in the form of linear combination of the output of kernel function. Okay, so please remember this sentence. I'm going to specify the detail later. let's move to dual representation. Dual representation. Separate vector machine or kernel machine can be used for regression or classification. So to begin with, let's consider a regression problem. In the second lecture this semester, let's consider sum of square error and a regularization term to derive a linear regressor. So let's consider this objective function again. The objective function is denoted by J of W. It means that the objective function is controlled depending on the value of the learnable parameters W. Okay, so the first term is sum of square error. We consider the square difference between ground truth and the regression result. We consider a linear regression problem. So we firstly use some nonlinear basis function to project the data. Phi of xn is the projected version of data point xn. W is the weight vector. We calculate the inner product between W and the phi of xn. This is the regression output. The second term is the standard regularization term. It is W transpose W. Lambda is a hyperparameter. Lambda is non-negative. It is used to control the relative importance between the two terms. Okay, so this is the objective function. In the second lecture or in the first lecture, we say how to determine the optimal value of W. The optimization technique is to set the derivative of this objective function with respect to learnable parameters W to 0. We will get a closed-form solution. This is the solution. Okay. I write down the optimal solution in the top of the slide. Let's analyze the property of this optimal solution. Okay, let's look at the term inside the parentheses. The first term is inner product, so it is a real one-dimensional real value. Tn for regression problem is also a one-dimensional real value. Okay, so the term inside the parentheses is a one-dimensional real value. It is one scalar. Lambda is a predefined constant. So -1 over lambda is also a constant value. If we merge this constant and the term inside the parentheses, we use an. To denote their combination. That is the constant multiplied by the term inside the parentheses. So it is a real value, one-dimensional real value. It is a scalar. So from this equation to this one, what do you find? What do you observe? W is a linear combination of the training data. The optimal solution of W is informed of a linear combination of training data. So if we want to have a compact representation or metric representation, we use a capital Phi to denote the data matrix. As you could see, capital Phi by definition is a low-wise concatenation of all the training data. Bold A is a vector. It is a concatenation of the combination coefficient. So W is capital Phi transpose A. So this is the after analysis, we can realize that the optimal solution of W is a linear combination of training data. And it can be compactly represented in this form. Phi is the collection of training data. It is not a learnable parameter. It is fixed before training. So it is fixed during training. So the learnable parameter becomes A. So W is further controlled, or W is parametricalized by the vector A. If we want to learn W, it is okay as what we did in the second lecture. We directly learned W. However, according to this equation, you can realize that it is equivalent to learning W is equivalently to learn A. So it is the so-called dual representation, the dual representation of W. So in kernel method, instead of working with W, we reformulate the sum of square error algorithm with respect to the parameter A instead of W. We will talk about the advantage by so doing. Given rise to dual representation. So this is the meaning of dual representation. We are dealing with a regression problem. Originally, we learned W, but in dual representation, we learned A, and the A is the combination coefficient of the training data because optimal W lie in the linear combination of all the training data. Okay, so previously we say J of W is the sum of square error, regularized sum of square error. In dual representation, W equals phi transpose A. So we use phi transpose A to replace W, and we substitute this equation into J of W. We will get this one. Let's look at the definition of J of W. J of W is the regularized sum of square error. W now is replaced by phi transpose A. We use phi transpose A to replace W. So we will get this equation. Actually, it is equivalent to the original one. Here, phi is the data matrix. A becomes the learnable parameter. Bold T is the concatenation. It is a vector constructed by concatenation of the ground truth of data points. If you look at this equation, this objective function, you will find that phi is present in this equation in the form of phi transpose. So let's define a matrix called the kernel matrix. A kernel matrix by definition is phi transpose. Let's look at the definition of capital Phi. Capital Phi is law-wise concatenation of all the training data points. So what is the meaning of phi transpose? Actually, the size of K is n by n, where n is the number of training data. We calculate the pairwise inner product of the projected data points pairwise, their pairwise relationship. So kernel matrix K is n by n symmetrical matrix. Let's look at the element nm, the nth row, the element in the nth row and the mth column. Actually, it is the inner product between phi of xn and the phi of xn. So we use capital K to denote the matrix, kernel matrix. Kernel matrix with some subscript, it is used to index some particular element of this kernel matrix. We use lowercase k to indicate the kernel function. Kernel function is applied to data points in the input space. We would like to specify their relationship later, but by definition, kernel function is applied to a data point in the input space. And the kernel matrix K, by definition, store the inner product, pairwise inner product of data point in the feature space. OK， 在这一页投影片里面简单来说，我们就只是讲了，就是一个很重要的简单来说，我们就讲了一个重要的观察，就是呢，在这些线性回归的这些模型里面如果你用了一个就是 regularized sum square error 的这种方式的话，它的最佳解就是呢，这个 W 最佳解呢，其实就是所有的资料的线性组合而成。那根据这个数学式，我们把它带进去原来的这个sum of square error， 你这个时候会发现就是说呢，我们从原先的要学习的变数从 W 转换成 A， 那这个不是标新立异，等会我们会就是说我们在下个礼拜会去讲这个做法呢，它其实会带给我们很多的好处，也就是所有的 kernel method 的这些那么 popular 的原因。那在这个情况之下呢，你把这个 phi transpose A 呢带进去原来的 sum of square error， 你会发现就是长得像这种形式。那这边呢，所有的 phi 出现的形式呢，都是以这种 phi phi t 的这种 phi transpose 这种方式呈现的在所有地方都是以这种方式呈现的。所以呢，这个 phi transpose 呢，我们就把它定义成一个 kernel matrix K。为什么呢？K 呢其实是一个 n 乘以 n 就是资料的点数乘以资料的点数的一个 symmetric 的一个矩阵。那它呢就是来记录呢这些资料点之间两之间的关系什么关系呢？根据这个定义它的 nm 这个 nth row zth column 这样子的这个 element 呢，其实呢就是在根据这个定义的话呢，就是呢这两个资料点呢，dn 笔资料跟 dm 笔资料，它们在 feature space 上面的内积。然后呢，我们之后会讲就是说我们希望去设计一个 kernel matrix、kernel function， 用小写的 k 来代表。那它是作用在这一个原来的 input space 上面然后它就可以得到这个像这个内积的结果。那这个叫做 kernel function。那因为时间的关系，我们要公布作业3。那不晓得这个 dual representation 跟这个 kernel function 或 kernel matrix 的意义，大家有没有什么问题要问的？In the following, we are going to announce homework number 3. Before announcement, do you have any question about dual representation or the definitions of kernel function or kernel matrix? Okay. Jimmy, are you ready?
Yes.
Okay.
老师可以开共用给我吗？那个开我好像没办法共用我的桌面。 喂，
你可以试试看，现在
有
也可以。
哦，可以了，可以了，可以了。Okay, so can you see my screen and hear my voice?
Yes.
Okay, okay. Hi everyone. So I'm TA Jimmy. So in the following slide, I'm going to announce homework number 3. So the deadline of homework number 3 will be May 4th. So it's as usual, you have 2 weeks to finish this homework. And we also have the 2 part of this homework. We have the code assignment. You need to implement the decision tree, data boost, and random forest by only NumPy. And also you need to answer some short answer questions. So please remember to submit your code and your report on the UC system. So you can find the sample code and the questions through this link. 那大家好，我是 TA 居民。那这个slide我们会公布这次的作业3。那作业3跟往常一样，就是我们会有2周的时间让同学来完成。那同时会有2个部分，第一个部分是 coding 的 assignment， 第二个部分是简答题。那这次的 code 会请大家实做呢，老师今天教的 decision tree、data boost 以及 random forest 的这3个演算法。那这个是只能使用 NumPy 来实做，所以你不能使用 scikit-learn 任何套件。那当然，如果你在实作上有问题的时候，你可以参考一下 scikit-learn 或是其他网络上的 tutorial 是怎么样去写这个 decision tree 的。但是记得就是你们要使用 NumPy 去实做这3个演算法。那在上传都记得要如同之前讲，你们的档案要按照我们这边定的那个 file name rule 这样，不然会扣一些分数。Okay, so basically the decision algorithm is trying to find the role to split your data. So suppose we have some example. So suppose a bank want to whether to approve the loan for a customer. So he follow the previous history data, and if he found that if this customer he has the length of current employment over the 1 year, so you will approve the loan for this customer. So the question is how do the bank find this rule? So in the decision algorithm, you will basically want to find a feature to make the decisions. So you want to find the features that can split the data. After split the data, the class and the resulting node are as pure as possible. So you can think that the bank use the history data and find that if the customer have the length of current employment over 1 year, they will always pay back their loan. So in this feature, you can use this feature to predict the to make the decision for the incoming customer. Okay, so the question is how do we measure the pure? So we have 2 index. First one is the entropy, and the second one is the Gini index. So in your homework, you will need to implement both of these instead to calculate your pure measurement. And after you find the pure, after you can measure the pure, you can how do we find the best split? So suppose we have like 2 features, the A feature and B feature, 2 ways to split the data. So the A ways and B ways. So after we split the data by the A ways, you can see that we can calculate the data class distribution in each node. So we can use this distribution to calculate the Gini index to measure the purity of this data. And we find that we want the Gini index to be smaller the purer. So we want to find that using the B way to split the data, we can get a lower Gini index. So the B way is better than the A ways. OK， 那这边我用中文再快速的再简单一下，不过这就是基本上就是一个decision tree的演算法。那我们就是想要去透过历史资料去找寻说我们要怎么样去对资料做切分，才可以让未来这个模型可以应用在测试上面的时候，可以让模型有很好的效果。所以这边有个例子，就是我们银行要不要贷款给一个 给用户。那我们可以参考历史资料去看，发现说，如果在历史资料上面有工作时间超过1年的用户，通常都会还贷款。所以根据这个资料，我们就可以就用这个规则去说，让未来的用户，如果我们去观察他的工作时间有超过1年的话，我们就可以核准贷款给这位用户。那要怎么样找到这个特征？就是为什么是1年？那为什么是用这一个工作的时间来判定的话，就是说我们从历史资料的话，我们可以去进行它的切分。我们可以将历史资料里面所有有贷款、有准时还款跟没有准时还款的人，把他们的特征找出来。那我们发现说，这个特征可以很有效的区分说会还贷款跟不会还贷款的人。那这样的特征就可以很有效的来帮助我们做一个判定。那我们要怎么样去衡量说这个切分之后的 data 它的分布是非常的干净的？那有 entropy 跟基尼这2个 index 来使用。那在作业中也会请同学去实做这2个计算purity 的function。那在你实做好这个方程之后，接下来你要怎么样定义说哪一个切分的方法可以让你的资料切的比较干净点？那基本上就是你是 loop 所有的 feature 以及它所有的值之后，那去找寻说哪一个切分的值以及哪一个切分的 feature 可以让你切完之后的 data 能够更是类别都是属于同一个类别的话，那就代表说那个切分的值跟它的 feature 是很有效的。Okay, so the pseudocode of diffusion tree is quite simple. So until you stop, you just select a node and loop all your values of all features. And then you partition the node and calculate the purity of the data by the Gini index or the entropy. And then you find the value of feature that can L the lowest value of Gini and entropy. And this is the feature to speed. You can use this feature to speed this node. So you go to next node and repeat that to see. So if you don't set any starting criteria, the data in each the starting criteria will be only if the data in each node belongs to the same class, the decision tree will stop growing. But so you can pre-specify some limits. You can retrieve the depth of the tree, and then the distribution will not start growing at some certain node. 那这边就是列出了底区的 pseudocode， 其实概念是比较简单，就是在选到一个 node 之后，接下来就是把所有的特征以它的值全部 loop 一遍之后呢，去计算说每一个值切分出来的 data 它的 purity 跟它的 purity 如何，那去找到找到那个特征可以让你切出来的值最小之后呢，你就可以使用这个特征来切分这个资料。那切完之后就是可以进行在下一个 node。那在底圈区它什么时候会停下来的时候，只有在所有的 data 在每个 node 上面都是属于同个 class， 又或者是说它达到了你指定的一个限制，就是说你希望树的深度不能超过某个值的时候，在这个时候底圈区才会停下来。So if you do not set any limit such as depth of node, the distribution can find a unique path for each data. So in this way, you can somewhat observe the overfitting problem. So there is an ensemble method of distribution tree to avoid this overfitting problem, such as bagging and boosting. So in the bagging, we will require you to implement the random forest algorithm. So it's basically just feed many deep trees to bootstrap resemble version of the training data, and then you can classify the data by the majority voting. So you will grow the tree as many as you decide, and then for each distribution tree will output for a certain class, and then you just use the majority voting to derive the final class. So where's the randomness of this forest? So just as the Professor Lin mentioned, you will need to bootstrap the data set, and each tree you will go with different data and the different features. So which features or data to be used are randomly simple to grow a certain tree. So you can see that the tree 1 and the tree 2, they are all grown from the different data sets. So their prediction will also be different. But after you grow many trees, you use majority voting to decide your final classes. 那这边就是除了在底圈区训练完之后，会有 overfitting 的 problem， 所以这边会请同学实做另外一个 ensemble 的 method 就是使用 random forest 的方式。那 random forest 就是它基本上会生成很多的很深的树。那在这个每棵树的生成是使用不同的特征以及不同的资料所生成的。那这样的话就可以在使用不一样的资料产生出来的树，最后进行平均之后来缓解 differential overfitting 的问题。And there's also the boosting problem. It will iteratively fit many shallow trees and get a result by weighting those classifier. So this detail has already been demonstrated in the class slides. So you can refer to the ADA boosting. So in this homework, you need to implement ADA boosting by using the teacher tree as the base learner. 那在第二个 ensemble method 除了老师讲到的 bootstrapping， 还有一个 boosting 的方法，就是 ADA boost。那boosting 就是会在每一个不同 iteration 里面去实做不一样的 weak classifier， 然后就用 weighted 的方式把它们的 prediction 结合在一起。那我们这边的作业会请同学使用你第一题已经做好的题选区当做你的 weak classifier， 然后看看这个 ADA boost 的效果能不能比题选区来得更好。So for the coding assignment, you need to make sure to comment your code. So I just want to notice that in this homework, the complexity will be like more complicated, more complicated compared to the previous homeworks. So you need to make sure you need to document you need to document each step of your model. So otherwise, if TA cannot understand your code, we cannot score your code. We need to make sure that your function implement all the component we want. 那这边有特别注意，就是在这一次的作业里面，因为要实做3个演算法，那每个演算法里面其实都有一些细节在里面。那比如说，我们会希望同学要实做一些，比如说我们会叫你们实做一些 argument， 比如说你们要指定树的深度是多少，或是有几个 base learner 的数量有多少。那这些东西必须要清楚在你们的 code 里面有写出你们实做这些演算法的步骤，那让助教可以确定说，你们这个东西是有正确实做出来的话，我们才可以给相对应的分数。So the late policy will, as usual, if we will deduct the late 20 points per additional late dates. So here's a notice: all of your models should get an accuracy over 0.8 on the provided test set. So if your model fail on this number, you may have some problem implementing your algorithm. So if you have any questions or comments for the homework, you can feel free to mail me and CC Professor Lin. 那这边要特别强调，就是在这次作业里面，助教测试过说，在这个 test set， 你使用正确的 decision tree 跟 ADA boost 跟 random forest 都是能够超过，在 test set 上面都可以达到 accuracy 超过 0.8 的。所以如果你们的 model 在实作出来之后，发现 accuracy 是小于这个数字的话，那很有可能就是实作上面有错误，所以你们要去找到说可能的 bug 原因是什么地方。Okay, so let's see for the homework number 3. So I'm going to go through the detail of this homework. Okay, so here's the document of the homework number 3. So the deadline is May number 4, and you can see that here's this is a sample. You can find the sample code and the data on the GitHub page. So for the first question, you just need to find the Gini index or entropy. Here's a provided function. You just implement this to calculate the Gini index of this array. And the second question, you need to implement the distribution tree algorithm. So you can see this link for the details. And you need to implement 2 arguments for this distribution tree. The first one is the criterion. The criterion will be could be Gini's or the could be Gini's or the entropy. So you can this argument will let the user to select which function to measure the quality of the split. And the second argument will be the maximal depth of the tree. So if the max depth is equal to none, then the nodes are expanded until all lists are pure. And if max depth equal 1, you will need to split only once. So you will need to implement these 2 arguments, and then we will asking you to use different criterion or different max depth to show the accuracy score of your test data. And the third question is you can plot the feature importance of a decision tree model. So when we do the feature, when we do the data splitting, we will use a feature. We will use a feature to perform the data splitting. So if the feature is used used frequently than other features, and we can know that this feature is much importance in this task. So you can plot this feature importance to see your plotting figure will be look like this figure. You can see that its outlook is used more frequently than other features, so its importance will be higher than other features. Okay. And the fourth question, we will need to implement the ADA boost algorithm by using the decision tree you just implemented from question 2. So you just need to implement one argument for this algorithm, which is the number of estimators. So and then you show your test score by an estimator equal to 10 or equal to 100. And the fifth question, you need to implement a random forest. And in this algorithm, you need to implement 3 arguments for the random forest. So the first one will also be the n estimators. You will need to define the number of trees to grow in your forest. And the second question will be second argument will be the max features. It is equal to the numbers of features when we looking for the best leap to consider to when looking for the best leap. So just as mentioned, the data and the feature to use to grow a tree in the random forest is different in each tree. So the max feature just denotes the number of features to use. So if you do not, if this max feature is equal to the all features, so there in this way the randomness of feature is disappear. So so usually the max feature will be like a square root of the number of all features. And then the bootstrap denotes whether to bootstrap the sample and use to building a tree. So in the random forest, we use bootstrap to sample the data and then generate the new version of data which is different in the each tree. So the final question is you need to like tune the hyperparameter or perform the feature engineering, try to get a higher accuracy score. So you need to screenshot your test score on this report. And please note that only the ensemble method can be used in this question. The neural network is not allowed to use in this homework. OK，so 我这边这样中文很快速的再讲一次，就是这个作业这一次的作业细节的话，一样是就是5月4号2个礼拜时间。那在资料集跟 sample code 都可以在这个GitHub 链接上面找到。所以基本上就是同学要实做，刚刚讲到的今天是跟 entropy 一个function，然后还有 decision tree 跟 ADA boost 跟 random forest 这三个演算法。那这每个演算法里面呢，我们都会要求同学去实做一些我们指定的 argument， 就是那其实这些 argument 跟那个 scikit-learn 的 argument 基本上是也一样的。所以如果你真的写不出来，你可以参考说 scikit-learn 到底是怎么样实做这些 argument 的。那这些 argument 就是让 user 能够去选说，我今天想要用不一样的吉尼index，不一样的 criterion， 或是我的数有指定的深度的时候，那这些参数呢，你会发现用不一样的参数去跑在训练集上面，都会得到不一样的结果。所以最后一题的话，会希望同学可以去测试看说哪一种参数的组合，那或者是哪一个演算法可以让你们得到一个最佳的效果。那如果我们在所以第二题的话，就会以同学的分数来决定说你这一题应该拿到的分数是多少。Okay, so as usual, we have 2 short answer questions. So just write down your answer and then paste on your report. All right, so I think that's it for the homework number 3. So just as mentioned, this homework is more complex than the previous homework and is also much heavier. So you need to like start this homework, start to write this homework earlier. 那这次作业就是相对于作业1跟作业2是稍微比较复杂一点，而且分量也稍微多了一些，所以会建议同学尽快的开始尽量实做这次的作业这样。那就是这是作业3的公布，同学有任何问题吗？
大家有什么问题要问TA 的吗？除了 Jimmy 以外，其他的 TA 也在哈。那看大家对于Homework 2的那个分数有没有什么疑问，也可以问这样。OK，如果没有问题的话，那我们今天的课程就到这边。About time. See you next week.